For joining this second day of the Einstein Toolkit meeting that Rahima and Behan led so well yesterday. I hope that you're looking forward to another day of talks. We're kicking off this morning with Philippe Grandclement from the Meudon Observatoire, a developer and expert in initial data systems from Lorraine to Cadath and additional codes, who's going to talk about initial data for binary systems. So thank you, Philippe.
Okay, thanks for the invitation. So I took a semi-historical approach in this talk. So I will start from the very early works from the 60s and try to move through the various incarnations of initial data generated for binary systems up to the up-to-date data. So we'll start with the 3+1 formalism. So I will go very quickly because I think you had a talk about that yesterday. So just to be on the same page. So 3+1 formalism, essentially you split your spacetimes into a set of spatial hypersurfaces, meaning that at each point, the normal to the hypersurface lies inside the light cone. On each hypersurface, you define a purely spatial coordinate system. So R, X, Y, Z, R, theta, phi, stuff like that. And then you add to this purely spatial coordinate system a label that tells you on which slice you are. And this label is T, and this is the time. So doing that, you reconstruct a full coordinate of space-time. There are various quantities that you can now define and that are very useful. Essentially, you can say that this n here is the lapse function. It's essentially the temporal coordinate of the normal, and the spatial part of the spatial component of the normal is described essentially by something which is called the shift. And the names come from the fact that if you consider two neighboring slices, and if you consider an Eulerian observer, meaning an Eulerian observer is someone which is moving along the normal, so it follows this line here. So you see my mouse, don't you? Yeah, okay, good. And so the proper time measured by this observer between that slide and this one is just the lapse times the change of the lapse times the change of time coordinates. So, and essentially the lapse tells you how the time is measured by an Eulerian observer. Concerning the shift, it describes the difference between the Eulerian observer world line and a spatial constant coordinate world line, which is this line here. And this is the difference between those 2 points is described by the shift. So the shift, in a sense, is a choice of spatial coordinates, whereas the lapse is a choice of time coordinates, if you wish. Okay, so now that you have that, you can project each index either along the normal. It's given by here. So you take the scalar product of, for instance, a vector with the normal. But you can also define the projection on the hypersurfaces themselves by using this projection operator here. And to do that now, you contract this gamma by your vector by this gamma. Doing all that, for instance, if you take the four-dimensional metric and you project both indices on the normal, you end up with what is called the induced metric, which is the first fundamental form. And the thing to know is that once you know the lapse, the shift, and the induced metric, you can reconstruct a full four-dimensional metric by this expression here, which is the standard 3+1 expression. Okay. So as you may notice, there is here this first fundamental form. So probably there is a second fundamental form somewhere. And this is the extrinsic curvature tensor. And it describes the part of the geometry that is not described by the induced metric. So it describes, if you want, the way the slices, the hypersurfaces, are embedded in a full spacetime. And essentially, they describe how the normal change on the hypersurface. So essentially, you take the covariant derivative of the normal and you project all that on the hypersurface. And you get this expression here. This is a symmetric purely spatial tensor, which is called the extrinsic curvature tensor. This expression here is not something we use a lot in 3+1 framework, but if you use a 3+1 framework with the laps, the shifts, and stuff like that, you can re-express these equations into that expression here, which tells you that essentially the time derivative of the induced metric is related to the extrinsic curvature tensor. And this extrinsic curvature tensor is known as the second fundamental form. Okay, so and just to finish with the 3+1 equation, the game now is to take Einstein equation and to project the indices, mu and u, either on the normal, along the normal, or on the hypersurface. So for instance, if you project both indices on the along the normal, sorry, you recover something which is called the Hamiltonian constraint equation. If you project one index along the normal, the other one on the hypersurface, you get a vector, a spatial vectorial equation, which is the momentum constraint equation. And if you project both indices on the hypersurface, you get the famous evolution equation, which tells you how the extrinsic curvature tensor varies from one slice to the other. The E, P, and S here are just projection on of the matter term, which is I will not discuss right now. Okay, so what is interesting for us here is that you can split the 3+1 equations into a set of two families. The first one are called the evolution equations. Actually, that's the second ones on this slide here. So that's here. So it tells you how the induced metric and the extrinsic curvature tensor evolve from one slice to the other. The first one here is just a definition of the extrinsic curvature tensor, and the other one is the evolution equation. On top of that, you must add two equations that do not involve time derivative, which are called the constraint. That's the Hamiltonian constraint and the momentum constraint. And you can do an analogy with Maxwell equation in that case. And so if you want to do a simulation of in numerical relativity using this framework, you have actually a two-step problem. The second step is called the evolution problem, when you start from an initial value for the induced metric and for the extrinsic curvature tensor, and you can use the evolution equations to get the values of those fields at later times. So I will not discuss this part here, but that's not the end of the story. Actually, that's not the beginning of the story, because at the beginning of the story, you must solve the initial data problem, meaning you must solve these two constraint equations. If your initial data, so your values of the fundamental forms at t equals 0, do not solve the constraint equation, then in the end, you will not get the solution of Einstein equations. So that's different from Newton's case. In Newton's case, there are no constraint equations. You can take whatever value for the velocity and the position and get a valid solution. That's not the case here. So you must solve the constraint equations. It's a set of 4 highly coupled elliptic-like equations. So it's not that easy to solve, as we will see. So it's not easy to solve from a mathematical point of view, and it's not always easy to make the link between the mathematical solutions and the physical situation you want to describe. So if I tell you, give me the extrinsic curvature tensor describing two black holes on an elliptic orbit with an eccentricity of 0.7 and a spin, and it's not that easy to translate that directly into what the value of Kij must be, for instance. So that's another difficulty. So that's the setting. I will now explain how we can try to solve those constraint equations. And I will focus first in a case of two black holes, so no matter, empty space and containing two black holes. So we'll start with what is called the static solutions, and it's a very simple case where you consider only solutions for which the extrinsic curvature tensor is 0. If you do that, it's the momentum constraint equations that you see here is automatically trivially satisfied, and you just left with the Hamiltonian constraint equations. So it's relatively easy. And what you do most of the time, you do a conformal flatness approximation where you state that the extrinsic curvature, the induced metric relates to the flat one, Fij, by just a conformal factor. So as I said, with this setting here, the momentum constraint equation is trivially satisfied, and the Hamiltonian constraint equation reduces to the fact that the flat Laplacian of this psi here must be 0. So you just have one equation, which is a flat Laplacian of psi that must vanish. I must say also that it's not very physically meaningful in a sense that setting Kij equals 0 means that your two black holes essentially have no initial velocity. And so if you do a time evolution of such data, you will end up with having the two black holes do an head-on collision, which is not very realistic. Anyway, we must solve this equation. It's very simple. The trick now is how can I be sure that this spacetime, the solution, will contain two black holes? One of the possibilities was proposed by Brill and Lindquist in 63, and this is done by demanding that psi diverges at 2 points of your spacetime. So here, when R is C1 or R is C2, the conformal factor diverges. Okay, that's it. This expression here is obviously a solution of the flat Laplacian of psi being 0. If you look at this solution, there is obviously a first asymptotically flat region, which is a region when you're very far from the points of divergence. So if you make R goes to infinity, obviously psi goes to 1, and you have an asymptotically flat region. In this region, if you look at how psi goes to 1, you can define a mass. And in that case, the mass is just twice alpha 1 plus alpha 2. So those two alphas control the masses of the holes if you want. And C1 and C2 controls where they are. But that's not the only asymptotically flat region. You can actually do a coordinate change and see what happens close to the singularities. So if you go close to C1, for instance, by using this R1 and make it go to 0, you can then do a coordinate. You can introduce a new coordinate, R1 bar, which is just essentially the inverse of this R1. And so if you go close to the diverging point, meaning if you make R1 bar goes to infinity, you can show that this is also an asymptotically flat region, but this is linked to a different mass, which takes this expression. And essentially, you have three regions that are asymptotically flat, so far from the diverging points. That's the region here, and close to the 2 points. So you have three regions that are asymptotically flat. And you can see, if you look at the expression here, for instance, M1 and M2 are different, meaning that the regions close to one hole or close to the other are different. So we talk about a topology with three sheets. So three regions that are asymptotically flat, far from the holes, close to this one, and close to that one. So that was one of the, we'll come back to this three sheets topology later on. So very soon after finding this kind of solutions, people try to modify them to ensure, the idea was to ensure that the asymptotically flat regions close to the holes are the same. So they want to merge this part here and that part here. So essentially, it works like that. So it's due to Misner and Lindquist in 63. So the idea is to ensure that the two lower sheets are the same. So what you do, you consider two spheres of radius R1 and R2, and you define an operation which is the inversion with respect to one sphere, to a throat if you want, where essentially you just take the inverse of the radius. And the whole procedure, the idea is to make sure that if you do an inversion with respect to the first one or with respect to the second one, you end up at the same point. By demanding that, you can ensure that you have only two sheets. I will not go into all the details. It's not that interesting. It's not that difficult either. You can look at those two papers here. But in the end, what it changes from with respect to the previous solution, it just implies that the conformal factor takes the same form as before, except you have now a series of diverging points. So instead of having just two diverging points, you have an infinite series like that that converges. You can actually find analytic expression for the Cn and the Dn's, and you can show that by construction, in that case, you have only two asymptotic regions, and they have the same mass. And so the illustration is that expression here. So you have one asymptotic expression very far from the throats, from the spheres. But if you do an inversion with respect to one throat or the other, you end up in the same asymptotically flat region, which is here. So this is a topology with two sheets, and this is due to Misner and Lindquist in 63 also. Okay, there is, why am I talking about all those very old solutions? It's because they contain the same flavor as the simulations we do nowadays. You can actually show that the Brill-Lindquist, the Misner-Lindquist solution, so this one here, you can get it by solving for the constraint equation, that one here, only outside the throats. So you can solve that only in the region outside this sphere here and outside that sphere here. But you need to prescribe some boundary condition, non-trivial boundary condition on the spheres themselves. And because of this inversion, you can show that on the spheres, the conformal factor must verify some kind of Robin-like boundary conditions. And actually, you can show that this condition here is equivalent to demanding that the spheres are apparent horizons. So in the case of Misner-Lindquist, you can think of the problem being the following. You give yourself two horizons, the red and blue spheres, and you solve for only outside of those horizons, and you impose that the spheres are apparent horizons by demanding that the conformal factor obeys a very particular boundary conditions on the spheres. So if you want, the Misner-Lindquist data corresponds to what we call the excision method, where you solve the equations only outside of an apparent horizon, and you impose at some conditions on this apparent horizon. On the other end, the Brill-Lindquist data, you solve in the whole space, but on 2 points. On those 2 points, you enforce divergence of the fields. This is what we call now the puncture method. So you see that even in 63, at the very beginning of solving these constraint equations, you already had the two families of methods, either the puncture one or the excision methods. And so they are already present in a sense in the very first computation of binary systems. I think that's why that's kind of interesting. Okay. So as I said, it's not very satisfactory in a sense that if you do an evolution of those initial data, you will get an head-on collision essentially, and that's not what you want to do. You want to be able to simulate black holes that go around quasi-circular and slow in spiral stuff. So you need, in order to do that, you need to go to non-static solutions. I'll check the time. I think it's okay. So the idea now is to have solutions with a non-vanishing extrinsic curvature tensor. If you consider first a single black hole, the momentum constraint equation takes this form here, and actually, as it's a relatively simple equations, all the solutions to that equations are known, and they are analytic, and they have been classified and shown. And essentially, they can be split into two parts. There are some solutions that contain a linear momentum. So we think they're going to describe a moving black hole. And some are associated with angular momentum. So meaning they are going to describe something that rotates. I'm not giving the actual expression there. They can be found. And the idea, as the momentum constraint equation is linear, is to combine such solutions to get something that you hope is meaningful, meaning that something that will represent black holes on a quasi-circular orbit, for instance. So yeah, so it's all based in the fact that you know all the analytics, all the solutions to that equations, and you know them analytically. So the generalization of the Brill-Lindquist data to the non-static case is called the puncture method. As I said, it's due to those people at the end of the previous century. And the idea is to set an analytic expression for the extrinsic curvature tensor of that form here. So you see that black hole 1 and black hole 2 have both linear momentum, and you enforce that they are moving in opposite directions. So I don't know if you see my face, but the two black holes are moving like that as they are, as if they are on a circle, if you want. You can add some spin contributions if you wish. So all this is an analytic expression. Now, in order to retain the flavor of the puncture method, meaning that you want the conformal factor to diverge, you assume that it has this form here. So the diverging part is contained into this B factor here, and it's enforced to be analytic, and take this expression here. And what you do, you solve the Hamiltonian constraint equation, which is the only equation that remains, for this U, which is the regular part of psi. So you take out the diverging part of psi analytically, and you solve for this U in order for the constraint equations to be fulfilled. In that case, the constraint equation takes this form here. It looks like a Poisson equation as before, except due to the presence of the extrinsic curvature tensor, you have this additional term here. And so once you know U, you can reconstruct your full solution. A bit, uh, uh, people also try to play the same game, essentially, but apply that to the Misner-Lindquist data. So the idea is to start from the same kind of expression for the extrinsic curvature tensor. But once again, you want to be sure in that case that when you transform your upper sheet into the lower one, you get only one expression. So essentially, you cannot take this K directly. You need to slightly modify it using the inversions with respect to the sphere. Once again, it's not very important, but bottom line, you can still find some analytic expression for the extrinsic curvature tensor. And what you do next, once you know that, you solve for the conformal factor. In that case, it must verify this expression here. And as I said, in a static case, you solve for this equation only outside of the spheres, and you demand that the spheres are apparent horizon by this. So same expression, same method as the static case, except you have this second, this right-hand side term that comes from the fact that you have a non-vanishing extrinsic curvature tensor. So I think it's due back to Kulkarni in that case. Okay, so doing that, you are able to generate initial data for black holes that are not going to do an head-on collisions, but nevertheless, it happens that those initial data did not behave very well. And so they did not behave very well in evolution codes. It's not clear that the initial data was the only problem. It was the early days where there were a lot of things we needed to control more than we did at that time. But one of the problems, for instance, is that if you use those data and you compute some global quantities, like for instance here on the right, the left-hand side, you have the binding energy as a function of the orbital velocity and the total angular momentum as the function of the orbital velocity for the configuration of maximal, the last stable circular orbit, if you want. And in the if you use those data, you end up with values that are here and there. But if you compare that to post-Newtonian results, for instance, which are the circle here, you see that you have almost a factor of 2, essentially in terms of the orbital velocity. So to be a bit clearer than that, if you take those initial data and you compare to the post-Newtonian results, you have a very, you add at that time a very strong discrepancy. And so it was not very satisfactory. And it was not that clear at the beginning what was the problem. And it turns out that it's very probable that the problem comes from the choice of the extrinsic curvature tensor. So as I said, you chose expressions like that, but that's not the only choice you could do. You could take, change the factors in front, take various combinations of all that. So it's not the only choice. And probably what was done at that time was not the optimal choice. So we needed to do a bit better than that. And we moved to the extended thin sandwich approach. So the idea is the following. You start from what is called the conformal traceless decomposition. So you define a conformal, you define a conformal factor by this. So you extract a conformal factor from the metric. And by doing so, you can enforce that this tilde metric has the same determinant of the flat metric. So 1 if you're working in Cartesian coordinates, but other stuff if you're using spherical like coordinates, for instance. So you extract a conformal factor, and for the extrinsic curvature tensor, you extract both the trace, this k here, and the conformal factor. And you are left with this a tilde. So a tilde has no trace, and the conformal factor is reduced. The powers in terms of the conformal factor are not uniquely defined, and you can use other incarnations depending on your favorite choice. Okay, so using the definition of the extrinsic curvature tensor, you can show that this A tilde relates to the shift, the lapse, and the time derivative of this gamma tilde here. I'm not going into too much detail. So essentially, you extract the conformal factor and a trace. And the original thin sandwich methods is the following. You prescribe freely, so as you want, or as meaningfully as you can, some quantities, which in that case are the trace of the extrinsic curvature tensor, the conformal metric, the time derivative of the conformal metric, and the lapse. So you choose all those functions and you choose them in a meaningful way, if you want. And then the unknowns, the thing that you are solving for, are the shift vector and the conformal factor. And those quantities are subject to two equations, which are the Hamiltonian constraint and the momentum constraint. So that's the original thin sandwich method. So you choose those four quantities, and you solve for the shift and the conformal factor by solving for the constraint equations. It's valid, it produces initial data. The problem in that case turned out that it was not so easy to find a meaningful choice for the labs. So people came up with a slight variation of this thin sandwich method, which has been called the extended thin sandwich method. And the idea is the following. You are not considering only the momentum constraint equations, you're also considering a part of the evolution equation. And the part of the evolution equation you're considering is its trace. So you're considering the trace of the extrinsic curvature of the evolution of the extrinsic curvature tensor, and you're adding that to your system. It turns out that this is an equation on the time derivative of k, using just this here. And what it does is the following. Instead of, it changes actually the choice of freely specifiable variables. So essentially, instead of choosing the lapse, you're now able to choose the time derivative of k. The price you have to pay is now not only must you solve for the shift and the conformal factor, but you must also solve for the lapse. And you have one more equation, so you not only have the constraint equation, but you also have to solve for the trace of the evolution equation. But it turned out that it gave some better results. So maybe that's a bit, yeah, okay, I still have time. So now the game is, how do I choose those freely specifiable variables? That's the important part now. One of the things we do most of the time is we consider quasi-equilibrium configurations. So we consider that the two black holes are on quasi-circular orbits. So it's valid if they are relatively far apart and they are almost on a circle. And the advantage of doing that is that you can assume that there is an helical Killing vector. So if you want, waiting for time to pass is the same thing as rotating the system along its rotation axis. So I'm not going into too much details here, but essentially you have two sets of coordinates that you can consider. Either you're working with inertial coordinates. In that case, you have a Killing vector, which has this expression here. So moving with time is the same thing as rotating along the around phi. The fact that these inertials mean that the shift goes to zero at infinity. But you can also consider co-rotating coordinates where you move with the black holes. In that case, the Killing vector is just a time coordinate, if you want. And the price you have to pay that at infinity, the shift is no longer zero, but behaves like omega d over d phi. Actually, those two coordinates system are very easy to relate. And the only difference between those two lies in the shift, where the co-rotating shift and the inertial shift are just differ by this omega over d phi. Okay, so choice of specifiable variables. Most of the time we use maximal slicing. It has been shown to be relatively good for stability. So we choose the trace of the extrinsic curvature tensor to be zero. As we are working in quasi-circular orbits, we can state that we are in equilibrium, if you want, and so that the time derivative of k and the time derivative of the conformal metric are both zeros. So those four conditions are relatively sound and there are not a lot of discussions. there is a bit more discussion and to have on the choice of the conformal metric. Most of the time we enforce it to be flat. It's only true at 1p order, so it's not very strong. It's not valid a lot of time. For K, it's not true actually, but it does simplify the equations. It has the advantage of killing the gravitational wave emission at the initial for the initial configuration, and it is consistent with the helical symmetry. So people are trying to move away from this conformal flatness approximation with not much success yet, as I understand. But this is the weak point, I would say, about the method. It's this conformal flatness approximation. Nevertheless, it should be relatively true if you're far apart, meaning if your initial black holes are not too close. Okay, so what do
So,
you...
Philippe, could
Yes,
you wrap up in 5 minutes or so so we can take a couple of questions?
yes, I will try that.
Thank you.
So the resulting equation is a set of 5 elliptic equations for the lapse, the conformal factor, and the shift. And in my case, I do solve them using the excision methods, meaning I solve them outside of two spheres, and I enforce those two spheres to be apparent horizons. So it's a bit tricky, but if you assume that the spheres are apparent horizons in equilibrium, it leads to a set of non-trivial boundary conditions on the sphere. So for the lapse, the conformal factor, and the shift. At infinity, you enforce asymptotic flatness, very easy. And so you solve your elliptic equations between the spheres and at infinity. I will skip that. This is the kind of results you get for equal mass black holes. So the lapse, the shift, the lapse, the conformal factor, one component of the shifts. You see the two spheres here and there. So I solve the equations only outside of those two spheres. So this is a simple case. You can obviously have unequal mass binaries. You can have spinning black holes. I will forget that. If you do neutron stars, you can do almost the same thing, except you replace the non-trivial boundary condition on the horizons by matter terms. So I will not go into too much details here, but you can do that with matter terms. Some results. Okay, so one of the important fact is that for the first case, if you use all this setting, you do have results that match very well with post-Newtonian results. So it's a very strong indication that the initial data generated like that are going to be relatively good. Here you have, for instance, the 4PN results, which are the solid lines, and some results coming from the extended scene sandwich methods, both for binary neutron star and binary black holes. And you do see that in that regime, the agreement is very good. If you do an evolution of those methods, it also gives very good results. I will skip that. And so I will conclude by saying that this initial value problem has a very long history, so it takes back from the 60s. I think the problem is relatively under control since the beginning of the century. A big improvement has been coming from the use of the extended scene sandwich approach. And right now we have refined that, but essentially the method is the same. So by refinement, I mean the inclusion of spin, realistic equation of state, eccentricity reductions, and stuff like that. But the equations are the same. And I will stop here, I think, if you want to ask some questions.